Can you hear me all right? Can someone give me a thumbs up or tell me? Or...
Yeah.
Yeah, great, thanks. Great. Okay, so here we are. This is what we talk about really is down to you. So what I was going to suggest as a way of getting started is if you can use the chat, if you've got things, topics, questions that you'd like to go over, just write down what it is that you want to talk about in this session, and then we'll see if there's any common themes that are coming up a lot, and maybe start off by talking about those or reviewing those questions, and then beyond that, if there's any more specific questions, we can work through those. So can you start by doing that? If you've got questions or things you'd like to go over, just write down, broadly speaking, at least what it is, and then we can see what the majority of you want to look at and base it on that. That's great. So I'm going to make a note of these topics, see what's coming up. Check if I've got everything. So we've got stress concentration factors. Mounting sprockets. Okay, that seems like enough things, so thanks for those. Okay, so I think we've got a bit of a cluster of topics here about what counts as an iteration, how to present those, what to put in the report, and maybe this as well, what to include in the CAD. Then we've got some questions here about mounting things, and maybe something about the kind of the stress concentration factors and forces and so on. And then some things here about what you expect your design to be and whether it's too big or too small. And the safety factor, I think I can check what that was, but that was a more specific question, I think. So I suggest I'll start by trying to answer that, and then you can tell me if I've answered that or not. So the reports with the iterations, what to include. I think, you know, the first thing to say there is that there are the guidelines. Yeah, thanks for pointing out about the waiting room. I've left them out for a while, but I've just got them in and turned that off. So the first thing is this up. So the first answer to what to include in the report, how much detail to give, is this. I assume you've probably mostly already seen this, but just to check, if not, this is what I'm going to be looking for in the report. So have a summary of the rest of it. And then there's the two parts. The design iterations is about the process. So it's about showing that you started with something. It's showing that you understand where you are. You've started somewhere, which is this. Then you have an understanding of what you're trying to make better. So you're not just randomly changing things. Maybe you're trying to make sure that it can withstand the loads, or try and reduce the mass or something. So you start with somewhere, you say what it is that you're trying to improve. Then if you're going to do that, you need to understand what the mass already is and what the loads already are. And you then have a proposal for what you're going to change and show how it's either reduced the mass or it hasn't, or we've changed these diameters and now it works, or whatever, right? So that's the process we want to see. And just to make sure that we've seen that in a variety of things, then we want to have a range of possible changes. And we talked about in lecture 3 what kind of things that might involve. So hopefully that should explain what kind of level of detail we're expecting. So whoever said that it would be mostly figures, I think that's true. Figures are a really good way of showing things, sketches of what your diagram looks like. So I'll give you an example. We've said that the first iteration should be starting from, say, your initial layout that you come up with, and you've kind of done that by following my suggestions of what to use. It's just fairly simple with shoulders and circlips and nothing fancy. You've guessed some diameters to start with, and then if you do the analysis, you can show that that is not large enough to fail. So to do that, you probably want to include a sketch of what your layout looks like with some steps and diameters and where the things go. And then you will probably want to include a table or a figure that shows how big the stresses are at every node compared to the allowable stress. So you can see that, okay, my initial design maybe is okay in this part, but over here the stress is too high. Therefore, I need to make some changes. So then you go away and adjust your diameters in your spreadsheet, and you say, okay, we went away and adjusted the diameters. until we found this updated design. This is what it looks like with a sketch of the diameters. We had to maybe find some bearings now that fit that. We've checked that they're big enough to work, and now the stresses are all okay. So it's really that process. And hopefully it's clear in going that I haven't really asked you to provide all of the detailed calculations or the free body diagrams that you did at the beginning to back that up. It's about explaining that process. So for this part, we'll trust you that if you say this is the stress, then, and that's why we made this decision, that's fine. It's about the process. Then in the second half, it's the evaluation. This is about convincing someone that you've really done it properly. So here, this is where you'd be looking to provide some more detail of exactly how you've calculated those stresses, starting from the free body diagrams and what you've assumed about the forces and the loads, how you've solved those. You found some bending moment diagrams. You've used that to calculate the stresses and show that you've got that evidence that when you say the shaft doesn't fail, you've got the evidence to back that up. But that's only for the final design. Is that clear on the difference between those? Yeah. So yeah, the starting point for the initial iteration might fail because you just haven't thought about it yet. But I'd expect after the first iteration that you've adjusted things so that it doesn't fail. And hopefully that answers the question too about whether to include the initial design in the 5 pages. So the very simple initial design is your starting point for those iterations. But if you're including some more work that you've done within what you call the initial design, then you would show that actual work rather than guessing within your first iteration. There was a question about if you do that and you find that you have to change the transmission, I guess perhaps because you increased the diameters and it was then too big to work with that sprocket. I think that would be I'd say that would be a reasonable point to end the transmission. There's no definition of what an iteration is, right? It's a continuous process where you're kind of going round and round and changing things and trying to converge, where you should make big changes first so that it broadly works, but maybe there's some details that you need to go back and fix and eventually converge. So there's no absolute definition of what an iteration is. But in that situation, I'd say it would be reasonable to say, okay, we've updated our shaft dimensions, and now we've made the design so that the material doesn't fail. But we can see that that's now a problem, but it doesn't work with the transmission. So maybe the next iteration would be to review the transmission options and try and find something there that works, if that makes sense. So it kind of doesn't matter exactly. It's just about showing that you've gone through this process a couple of times. There were some questions about how much detail. I think I've hopefully already answered that. In your first iteration, do you need to have all the detail about exactly how the bearings are mounted? No, I think of it as that spiral. So we're trying to get started and figure out broadly what's going on by making some guesses and assumptions on getting started, maybe by assuming the stress concentration factors are just some standard values. And then we're kind of going round, and the later iterations would be hopefully making smaller changes that would not have to go back to the beginning and change nothing big. And equally, the first ones don't have to have all the details. There's a chance that you get through that process, and then you change something, you work something out that you think is just a detail, and if you're really unlucky, that could throw up some problem that's more serious and would require you to go back. So in reality, you might have to go back and start again. For this, I'm not interested in making you go back and repeat loads of work just for the sake of it because you were unlucky about something. So as long as you feel that you're demonstrating these criteria in what you've done already, that's fine to stop and say, we've improved it this far. We haven't quite managed to do that because of this unexpected thing. So as long as you can demonstrate those criteria in one way or another, that's fine. Okay. last iteration double as the final design? Yeah, so the end point of the iterations would probably be your final design. But if you want to keep making changes, that's fine. I don't need them to be exactly the same because you've got those 5 pages. I want you to use 5 pages to demonstrate that you're starting off somewhere and making it better, and then the second 5 pages to show that your final design really works. And if there's a gap in between where you could have written more about iterations but you don't have space, that's fine. You can do that if you want, but you don't need to. Okay. So then there's a few miscellaneous questions about whether things are too big or too small. Maximum shaft diameter, and there's no particular maximum. I mean, if it gets too big, then it's not going to fit in the components. And you do have a guideline, a wish in the requirements list that the spacing from the chassis down to the shaft is no more than 90 millimeters. So I guess that puts a hard limit on the diameter of the shaft at 180 millimeters, but obviously less than that in practice because you have the sprockets that take up space. But no, I wouldn't say that 60 millimeters was too big. It depends on what loading you've got. The loads you've got depend on what size transmission you've got, because for constant torque, if the diameter is smaller, you're going to get bigger force and bigger loads and bigger stresses. If you're using the less strong material, it's going to have to be bigger. If you're using the stronger material, it can be smaller. So there's lots of reasons why it might be different, but that's not unreasonable. Similar question about the keys, just checking that is coming out as a reasonable answer. Again, that will vary depending on what material properties you're assuming the key is. There was something about that on the forum if you want to look more about that. But yes, it's quite plausible that the lengths that you calculate for the key are fairly small. And that just means that the torques that the key is carrying are not that big. So even a very small amount of material would be enough to transmit them. And that is quite often the case. It's not always the case, which is why we have to check. But if the torques are fairly small, then that means that in reality, you're not going to have a key that's only 2 millimeters long, because that would be really fiddly and it would probably slip round if it was under stress, and you wouldn't do that. That's why in there's this guideline that it should be at least twice the width. That's just a guideline. In reality, if you've got a sprocket that's this width, then there's no real harm in having a key that's pretty much the whole width of the sprocket from end to end. And then you do the calculations to check that that's big enough. And if the length you find is much smaller than that, then the answer is yes, it's big enough. So you just go with that. Okay. So my next category of questions is about mounting things. So let's check what those are. Can we secure the sprocket in an axial direction with set screws? I'd say that's probably not a good idea. Set screws are only good for quite light loads. And again, if you have a look on the forum, there's some discussions about that, which all basically say the same thing. So how do we mount? You say bolt ball bearings onto the chassis for ones who don't have a chassis already. I assume you mean the bearing housings and how you connect that to the chassis. So we can look at that. Just check what the other ones were there. Potential choicing for bearing casings, that's the same. If we use a roller bearing, would we need a shoulder and a circlip as well? Yes, you would, to connect it to the shaft. A roller bearing is quite similar to a ball bearing, really. What you have in addition, though, is that, as you probably saw in the example I had, because it's rollers, then there's nothing to stop the two rings from sliding relative to each other. So you need to make sure that both the rings are attached, and you need to have some other solution to stop the whole thing sliding. So, for example, having a roller bearing at both ends would probably not be a good idea, because then the whole shaft could just slide out sideways. But at one end, that would be all right. For the requirements about the geometry, does it mean that both bearings must be within that width, or is it okay if we've designed it so that our bearing mount and bearing center lines are within that width? Yes, I think that's fine. Whoever wrote the requirements was obviously not careful enough about doing that, so that's something to bear in mind if you're ever writing requirements, to be specific about what you're talking about. But we won't worry about which way you measure that. Can we constrain a bearing with a collar with a grub screw? I think, as we said before, generally not a good idea unless you're dealing with very light loads. Okay. So let me sorry, let me just get the link that I'm looking for. So there was a question about mounting bearings. So I'll show you what probably the simplest way of doing this is. So this is what I had in my email. There's lots of different ways of mounting bearings in housings. If you look on the SKF, then they've got all of these different kinds: ball bearing units, roller bearing units. So these come with the bearing and the unit together, which is obviously simpler if they have something available that you can use, because you don't have to find two things that are compatible and put them together. But you can also get a range of housings that can be used with other bearings that you assemble yourself. But let's keep things simple. Look at these. So here it says ball bearings consist of an inset bearing mounted in a housing. So that's similar to the kind of basic deep groove ball bearing, but it's got a sphered convex outer surface on the outer ring that fits inside the housing. Because you have that curvature there, it means that if the alignment is not quite right, the bearing can rotate a little bit within the housing to accommodate that, which is useful. So here we have, there's two main kinds of these. So depending on whether you want to mount it on something perpendicular to the shaft or something parallel to the shaft, this is probably closer to the situation that you've got. And then there's all kinds of details there. But we're starting to get more specific here, that there are different kinds. So they're made of different materials. Some of them are made of pressed steel, but this is the simplest kind up here at the top, just a basic one. and obviously there's a lot there, but maybe if we want to start narrowing it down a little bit, and then we have that SY. Yeah, this can be quite useful to understand what all of these codes mean. So here, there's lots of variations here, but a pillow block housing or unit with a normal base, that sounds like a good place to start. To be honest, I don't know what all of these are, so I'm just kind of showing you my thought process for how I'd try and find something. So I'd start with something that seems quite short, but SY looks quite good. So let's try putting SY in there. And now we're getting somewhere. So there's lots of SY ones here. They've got different diameters. And then there's lots of different letters going on there. So I wonder what that's going on. The numbers of the size. And then down here, there's some extra letters. And then this tells you about what kind of bearing is on the inside. So for example, that SY20TF, the SY is the standard pillow block, the 20 is the size, the shaft diameter, and then TF is a bearing with set screws. So I think this is going to be something like the one that I've showed you in lectures, which looks like a pretty good starting point. So you can find some information out there, check what it looks like, get the dimensions. This will have the load rating data that you need, which should be pretty consistent with a normal bearing of the same size, but you can check that. And then if you decide you want to use that, you should be able to get the CAD model as well, which is useful for dropping that into your assembly. So I'd say, if in doubt, pick one of these that's the right size and just use that. Does that make sense? So then that's, as we talked about on Tuesday, in reality, you'd want to think about thermal expansion and whether it wants to be located at both ends or whether it can float. If you don't know what I'm talking about, you can go back and look at the lecture somewhere in the middle where we talked about that for a few minutes. But the idea is just that you don't want, if any expansion happens, for the shaft to be trying to expand against two bearings that are holding it in place. So you arrange for one of them to be firmly locating it and the other one having some freedom to slide. That means that the one that's firmly locating it, you would want to have a shoulder and a clip or some other way of securing it so that it's definitely fixed at that end. And then at the other end, you'd want the shaft to be able to move through. So in this case, because there's no possibility for adjustment around the outside because it's firmly fixed into this housing, you'd need to allow for that adjustment on the inside here, which means you don't need to put a shoulder right next to it, right, or a clip right next to it. It's located axially at the other end, so it's enough to just have it sliding through. It's a bit like if you remember solid mechanics, when you draw pictures of beams bending, normally you draw a little triangle with some hatched lines under this end that means that's firmly fixed. And at the other end, you draw a triangle with two little rollers under it that shows that it can move sideways. That's to make sure that it's statically determinate and you don't have to worry about whether it's being compressed together or not. You could, in theory, put the freedom to slide on the joint between the housing and the chassis. I think, yeah, I mean, you're right from the point of view of looking at the theory. I think in practice, you'd probably find that was more difficult and you'd have to worry about exactly how it would work in practice because you've got these two bolts. And if you were leaving them loose so that it could move, then it could twist sideways and rattle around. So I think in practice, the best solution is probably to slide on the inside, but that's a good thought. So I think that was those questions about mounting things, both onto the shaft with set screws, don't do that, and bearing housings onto the chassis and casings. So there was one other, let me just check if there were any other large categories of questions. I think that was all of the main things that we said. So I will just check through and see if there was anything that we haven't discussed yet. And I know there's a few new questions at the bottom, which we'll get onto if we've answered all of the ones above. Oh, bending and torsion, stress concentration factors was an early one. So again, there's different ways of doing this, and ideally, because you're trying to, gradually converge on a better design, but you don't know all the details to start with, you want to use the simple ways to start with and then improve it if needed. So the simple answer to how do you get stress concentration factors is to look it up in this table and use those numbers, right? So that's a good way to get started. This is not necessarily exactly matching your design, but when you're starting off, you probably don't know how sharp your shoulders are, or if you did, it would just be a random guess at that point because you haven't had a chance to think about that level of detail. So to start with, I'd use this. Then later on, if it's important, you can come back to this and check, for example, that the shoulder ones are matching up with the size of the jump, because the size of your shoulder might be bigger or smaller than this one, or sharper or more rounded, which will affect it. So then you can come back to these charts and look it up, or there are calculators online that I think we've linked to where you can put in the things and it does the calculation for you, but it's exactly the same as reading it off the chart. So I said you do that when it's important. How do you know when it's important to do that extra work? Well, one way is to think about whether the stresses that this stress concentration factor is giving you are actually affecting your design or not. So if you've got a stress concentration factor at a point where the bending moment is quite low, or where the diameter is quite big for another reason, then you've got a big margin between the combined stress you calculated and the allowable stress that you can have. Then even if you vary the stress concentration factor, it's still going to be below the allowable stress. It's not going to matter. Whereas at another point in the shaft, maybe your combined stress is big, and that in order to stop it failing, you've had to keep on pushing up the diameter at that point to bring the stress down. And then if you change the stress concentration factor, that's going to have a direct impact on how big your shaft needs to be to avoid failure. So at that node, at that stress concentration factor, it's worth coming back to it and looking again and seeing if the initial value you used was good, or if there's a way that you can change your design to reduce it. Design factor, the economic impact. I don't think it's, the question is, what is the economic impact? Is it the cost of replacing the shaft or the wider economic impact? It's a general approach really, so there isn't an answer to that. In general, I think you'd want to think about, you could take that to be from different points of view. It could be the impact on the person owning the bike if they have to replace a part. It could be the impact on the company if all of their designs have to be recalled and they have to replace them all, or they get sued because their designs were dangerous. There's no specific answer to that. From your point of view, it's not a major deal. You don't have the context to properly judge all of those factors to do this design project, because you don't have the background of the real company and what its situation is. So we're not expecting a huge amount of effort needing to be put into that, choosing a design factor. Just having a reasonable, brief reason for why you've chosen it is fine. There's question about what's included in the CAD. The question is the CAD part model including parts like the chassis? I'm not sure what you mean by the CAD part model, but I think the answer is probably no, because the part drawing and the part model is of the shaft itself. So that's what you've designed in detail, that's the part. Then the assembly drawing shows how that part fits with the other components. But because the other components aren't things that you've designed yourself, they're components that you bought from other places, you don't need CAD models or separate drawings of those, only as far as it helps you make the assembly drawing. Where's the forward force and weight loaded onto the shaft? On wheels or bearings? I mean, it will be a bit of both, because you've got the weight of the cargo going through the chassis onto the bearings, and then that's trying to push the shaft down, and then the shaft tries to push the wheels down, and the wheels try to push the road down, but so the road pushes back, and so the road is pushing the wheels up, and the wheels are pushing the shaft up. So you get a force down on the shaft where the bearings are and up on the shaft where the wheels are. The same with the forwards force. If the thing's moving forwards, the road must be pushing the wheels forwards, otherwise it would be going backwards. If the road's pushing the wheels forwards, that's going to be pushing the shaft forwards. And if the shaft's pushing the bearings forwards so that it can push the bike forwards, that means the bearings must be pushing back on the shaft. It's all equal and opposite reactions. Stress concentration factors for a keyway. You have again, I would say the first answer is just to use these values. Key seats are pretty standard. You follow the standard that tells you what shape to make them so that they're always pretty much the same. So you won't go far wrong if you use that. In slightly more detail, there's these charts that tell you what goes on based on some different studies that have looked at this in more detail. And they found that there's two particular places where the stress concentrations can happen: at the top edge on the surface here at point A, or at the end at point B. Are generally the places where the stress is biggest. And they say that the stress concentration at point A is generally 1.6, regardless of what shape things are. This is all just empirical stuff, right? Someone's taken some of these and done lots of measurements and said, oh, it seems to be like this. There's not really any more to it than that. So it's fairly rough and ready kind of thing. Whereas the stress concentration here depends on how sharp the corner is, which makes sense. And that follows this line. And generally you can see that that line is bigger than 1.6. So generally it's this point that matters. So it would be perfectly reasonable to just take one value at that point, and you don't have to worry about multiple stress concentrations at different points along it. Remember that this kind of approach to design is fairly rough. It's about doing that iteration and converging on something. You don't want to be doing a really detailed analysis every time of exactly where the stress concentrations in a keyway are. You want something that gets you roughly right the first time. And then when you converge on a final design, the next step after what we're doing would be to put it into a finite element model, probably, if it was something important that you wanted to check. If it was something kind of bog standard, low stress or low significance, then you'd probably be happy with these calculations, but you could always go back and look at this in more detail. So what we're going for here is not precise calculation of what the stresses really are. It's just, do we think that this design would fail or not? And if we can say it probably wouldn't fail, even if it's slightly over-designed, that's not the end of the world. So generally speaking, there's no need to get into too much detail there. If you're worried about where those nodes are in relation to where you've calculated the bending moments, so maybe if is the maximum bending moment at the middle of the keyway or at the end or at the other end, again, I wouldn't worry about that. If you've got a keyway that's this long compared to a shaft, the key's only that long, so that the bending moment's not going to change very much. So if you just take the bending moment that's the biggest value that's close to that in that area, use that as your bending moment, that's fine. It's going to be slightly conservative, but no one's going to mind about that, unless this is really causing trouble. And because you've made that simplification, you're finding that it needs to be really big, and then you could come back and revisit that. But 9 times out of 10, if you assume that, you'll be confident that it won't break because you've used a bigger bending moment rather than a smaller one, and it won't turn out to be a problem anyway. How do you draw up the iterations? There's no need to draw them up in Inventor, although you can. Once you've got Inventor set up, it might not actually be that hard to tweak the values and get those drawings out. So that's a perfectly reasonable thing to do, but there's no need. It can just be a basic sketch drawn out neatly by hand and scanned, or drawn out in another drawing program. Yeah, if torques are negative and the stresses you find are negative, that's not a problem. By the time you put it into the combined stress, that involves squaring it so that even if the individual stress components are negative, it will all come out the right way. And the question about key stresses. So the Keyway is to do with the nodes in your spreadsheet for looking at the shaft. The question is whether you have multiple nodes for the key and the Keyway. No, it's just the key that's in the shaft. The nodes are points along the shaft. We're calculating failure in the shaft material. The key is a separate calculation. If you look at sizing the key and calculating how long it needs to be, that's when you check whether the key material itself would fail. If you have a way of mounting a bearing that doesn't cause a stress concentration, should you still have a node there? I mean, it doesn't hurt. You could still have a high stress there even with no stress concentration, although it's less likely. So if you're not sure, err on the side of caution. It's only one more column in a spreadsheet, so it doesn't really cost much to do that. But if you think it's definitely going to be less stress than other places nearby, because there's no stress concentration, then there's no need to include it. End plates for the end of the shaft after the wheel. I have no particular recommendation about that, I'm afraid. I wouldn't worry about that too much. But if you ask that on the Q&A, then you can see if Speed has an opinion, because he probably does have an opinion about mounting wheels, and I'm sure he's right. Use a nut and washer to secure the wheel. Yes, you can. Search for that on the forum. There was a bit of discussion about that. You want to make sure that it doesn't rattle undone. Are circlips and shoulders the only method of actually locating a bearing? No, have a look back at the lectures. I think it was week 2 when we discussed that. Tolerance is the shaft and the inner diameter of the bearings. Yeah, the supplier recommends what tightness of fit to use, and then you can work out based on what diameter you've got, what the actual values are for that tolerance, as we went through in Tuesday's lecture. I'm not sure what the comment about outright 5 is. How can you use bearings against shoulders if the shoulders are rounded? There are some ways of doing that. So if you want to have a shoulder that's kind of rounded like that, so that it's got a bit of a radius there, and you're trying to do that because you want to reduce the stress concentration, then if you're trying to mount a bearing that has maybe a profile like this, then obviously if that size there is smaller than the radius, then it's not going to sit up against it nicely. So one thing you can do is to have a undercut like this, which means you still have a larger radius, but the component can sit up against it like that. Or you can have a what's called a stress relief groove. Which is actually cut into the back of the shoulder, but if you that has the effect of smoothing out the stress because it's starting to move it away from the shoulder a bit further back, which is only a very arm wavy answer, but you can do that. Or the other thing you can do is potentially put in a spacer ring. So if you want to have that big fillet, you can have a separate component that kind of looks a bit like that. And then you can slide it up against that so you still have the large shoulder. But those are all really details that it would be nice to think about, but is beyond what we absolutely need to do. So the safety factor, whether it's a very big value and where to discuss it in the report. Yeah, I think you're right. It seems like quite a big value, but also you could justify it. Again, what you do about that comes down to what impact it's having on your design. So if it's a big design factor, a big safety factor, but if you put that in and you work out how large your shaft needs to be, maybe you use a stronger material, then if that all works out okay, then maybe you were right, that's fine. If you do that and you're really struggling and it's coming out to need to be really large and that's making it difficult because it doesn't fit or it's too big for the transmissions and you're getting in, you're finding it hard to find a good solution with that design factor, you can come back to it and look at it again. So for example, one of the factors in it is to do with how confident you are on the material properties. And you might have said that maybe we're not fully confident about whether the material yield strength will be what it says it was. So we've ranked that less than very good, and that's contributed to having a larger design factor. But if you've tried to do it that way and you found that actually you're struggling, you want the design factor to be smaller, there are ways of doing that, which isn't just pretending that you're more confident than you are. For example, you could order more expensive material that comes with tighter tolerances on its properties, or when the material arrives, you could do some material tests to measure its strength and check that it really is as strong as it needs to be before you manufacture it into the shaft. And if you put those procedures in place, then that would be a good reason to reduce the safety factor because you've controlled those uncertainties. And similarly, there might be other ways of controlling some of the other factors as well. If you want to reduce them, maybe you can make changes so that even if something fails, it's not catastrophic, and then you would reduce the safety factor on how bad the consequences are. Or if you can make a change so that even if something fails, it's quick and easy to replace, then you could reduce the safety factor on the economic impact of a failure. Or, there's different ways you could do a more careful analysis in principle, although, as I said, I'm not expecting you to go away and do finite element analysis. So if you're going through that process of finding that something doesn't work and making changes, so that would be something that you could discuss in your design iteration section, right? Because you've recognized there's a problem, you're making a change and you show that that alters your design. So you could go through that process in your design iterations. You would also want to just provide the justification for your safety factor in the design evaluation as part of showing that your design wouldn't fail under the loads and those requirements. You don't have space to go into that in great detail. There's no need to regurgitate and repeat the kind of the background or the way in which, the general way in which you do the safety factor. Just include the specific things that you've done. Geometric tolerances, unfortunately, we don't really have time to go into that with everything else. That is something that the bearings catalogue will tell you about, recommended geometric tolerances for that, and there may be some others, about the bearings between two ends of the shaft. That's great to include if that's something that you've done. I know not everyone has covered that, depending on which unit you're on. Dimensions, part drawing, definitely. Dimensions on the assembly drawing, to the extent that they relate to requirements you're trying to demonstrate. And if you look through the slides from this week's lecture in the section on design evaluation, and there's some comments on that. Copy paste MATLAB or LaTeX, we need to be able to understand what it is. So you might need to prettify or comment on or rewrite your MATLAB code, depending on how clear it was to begin with. But there's, yeah, I think if done clearly, that could be a reasonable way of doing it. Doesn't matter what kind of nuts we use if we use them for mounting. You'd, again, as we said before, you'd want to be able to lock them to prevent them vibrating undone. Minimizing energy losses. The biggest sources of losses are probably either the transmission or potentially seals in the bearings. I think in the seal, there's a video on component selection about bearings that just talks about that very quickly, how there's different kinds of bearings that have a bit of a trade-off there. And if you look at the main types of transmission, they vary a bit in their transmission efficiency. So that's probably the major issue. We've already said it's okay if we choose a bearing housing for the final design only. Yep, that's probably reasonable. We need to add a brake in the shaft or plan for a brake to be added. I mean, in reality, that would probably be a useful thing, but for this coursework, there's no need to do that. It's not in the requirements list. And explain our calculations in detail in an appendix. I'd not particularly, no. I mean, I think what we really want is to have those page limits, those sections that we've already discussed that are in the design brief. That's what I'm expecting to look at. I wouldn't generally expect to look at appendices in any detail if they weren't part of the submission that was requested. Yep. Okay. Well, that was a bit of a whirlwind rush through those at the end, but it looks like we've got to the end of the list. Okay, so we've got another 4 minutes, so I'll try and answer your question about the free body diagrams. As a general answer, I think the question is about why the. Can you tell me if this is right? Is the question is about why, if the weights are acting on the wheels and on the bearings, where do they go on the shaft itself? Is that the question? So I'd think of it like this. You can draw lots of different free body diagrams, right? So if we drew, say, a rear view of the whole thing, where we've got some weight here, and it's connected through some bearings to a shaft, and then there's a couple of wheels on the side. That's on a road like that. That's the first step, is draw a picture of the thing. So if you wanted to then look at a free body diagram of the whole thing like that, then you draw it again. Yeah, Tim, I'm not sure what's going on there. I don't think we had anything scheduled, as far as I'm aware, apart from what I emailed about yesterday. Where does this which scheduled thing at 5:15 are you talking about?
So basically on our timetables, we have a slot from 5:15 to 6:15 every single week. But I thought that was now used. So I thought this week it was going to be used for this time, because normal we have not the slot for placement, that's after for me. So like normally our timetable says I have a
which program are you on?
Robotics engineering.
Okay.
So we have loyals the whole day, and we had a loyal from 4 to 5. That's why I assumed it would be just from 5 from 6, like it's on our timetables.
Okay, I see. Sorry for the confusion then. So yeah.
Is it recorded, the Q&A session?
This hasn't been, I'm afraid.
Oh, okay.
So, but I think you had another loyal at this time, which someone else told me. So, what I can try and do this time that we've just had was the only one that I could do at kind of short notice this week to fit it in with the timetable. But I'm sorry that didn't fit with your one. It's a question of the two different departments' timetables, I think, and as within the arrangements for the units, then because we have the 2-hour studio session and the lecture, then that was the 3 hours for the unit, and we weren't expecting to have any loyal sessions for the unit, but that obviously made it into your EE20223 timetable without me realizing to have that extra session. So I'm sorry for that confusion. It could be possible to have a follow-up session for you guys with the IME and robotics on Monday potentially, but yeah, that's the only other time that we could do it. But I can have a look at your timetable and see about that.
Yeah, okay. Anyways.
So I was just going to say, which I hope this answers your question, that there's lots of different free body diagrams, so we could analyze this one, and then we see that the weight is acting on the wheels, but then we could draw a free body diagram of the wheel itself, and we'd say, okay, we've got W/2 there, we've got the shaft here, and if this is a free body diagram of the wheel, then the shaft is pushing down on the wheel with some force B to balance that force up from the road, and for vertical equilibrium, V has got to be equal to W/2. And then if you drew a free body diagram of the shaft, then because every force has an equal and opposite reaction, then the force upwards on the shaft must be V. And if you kind of go through that process, then you find that if you draw a free body diagram of the shaft, you've got these bearings there. I'm just drawing these faintly to show where they would be, because they're not actually included in this free body diagram. Then you'd have W/2 there, and you can follow the same logic to show how that weight is acting on the bearings on the shaft. Okay, well, we got to the end of our time. I hope that was useful to go through some of those questions, and you're able to go ahead with developing your designs. All right. If there are other things, of course, you can ask on the Q&A forum. All right. Bye then.